Alright, so we're continuing on with section 7.8, improper integrals. Forgot to write this before I started recording. This is part 3. So we talked about the definition of, if I have an integral over an infinite area, how do I define that? How do I, evaluate it? We did a couple examples. Um, so one was, from I think 1 to infinity. The other was negative infinity to 0. This next example is the integral from negative infinity to infinity of 1 over x squared, 1 over 1 plus x squared dx. Okay. So you'll remember, so if you look back at the definitions, so they're in my notes, or hopefully they're in your notes. I post these notes now, so you can look at them as I'm, talking about things from different pages. So you remember that this integral, the way we define it is this is going to be the limit as, before we do the limit, we're going to break it up into two integrals, and you can break it up however you want. This is going to be the easiest thing to do. Negative infinity to 0, 1 over 1 plus x squared dx, plus the integral from 0 to infinity, 1 over 1 plus x squared dx. So the idea is you just break it up into two integrals like we've done before, and you're going to evaluate both of these. So let's go ahead and do that. So then this is the limit as t approaches infinity, the integral from, t approaches negative infinity. There's a way you can do it where they're both approaching infinity. We're just not going to do that. So t approaches negative infinity, t to 0, 1 over 1 plus x squared dx. And again, I know it seems superfluous to, change these into limits. It is important. You don't just want to evaluate things. You actually can't even just evaluate, negative infinity to infinity of that thing. Not without it, it's not going to make a lot of sense that way, at least. So we have, the first one plus limit is t approaches infinity from 0 to t. Sorry, can't talk while I write. From 0 to t, 1 over 1 plus x squared dx. And the good news is, both of these integrals, they integrate to the same thing. So this is the limit as t approaches infinity, negative infinity, of arctan of x evaluated from t to 0, plus the limit as t approaches infinity, arctan of x from 0 to t. So for this one, you need to remember, some of your values of arctan. So we're going to have then arctan of 0 minus arctan of t plus limit t approaching infinity, arctan of t minus arctan of 0. Good news is arctan of 0 is an easy one to remember. It's just 0. So this is the limit as t approaches negative infinity, negative arctan of t, plus the limit as t approaches infinity, arctan of t. And you can, so it's a good idea to have the graph of arctan memorized. It's one I actually have memorized. So it looks something like that. It's actually just one branch of tangent, rotated on its side. And so you have horizontal asymptotes here, top and bottom. So this is at negative pi over 2. This is at pi over 2. So that's one you want to remember. So then this is, as you go off to negative infinity, this is going to negative pi over 2. So this is negative pi over 2 plus, and as you go off to infinity, sorry, let me clean up that 2 so it's legible. It's really difficult writing on this, but it works, I guess. So and then the limit as t approaches infinity of arctan. So So if you look at this graph, I have t here. This is y is equal to arctan of t. So as t approaches infinity, this thing approaches pi over 2. So this is pi over 2 plus pi over 2. So this is pi. So again, that's interesting. We do this improper integral, and we get, this area is equaling to this area equals pi. It's the same area that you have if you had a circle with radius 1. And the graph of 1 over 1 plus x squared is going to look something like this. And so this whole area down here is, the same area of a circle of radius 1. That's pretty interesting. I guess if you're into that, which I'm majoring in math, so yes. Okay. So again, just make sure the hardest part of this is, converting these to limits. I know it does, seem like it takes, a stupid amount of time, but it's, what we have to do here. So let's move on to the next example. So this is a good example. So for what values of p does the integral from 1 to infinity 1 over x to the p dx converge? So you'll remember, the first two examples I did of this type of integral. First one was 1 over x squared. The second one was 1 over x. So if p is equal to 2, this thing converges, but if p is equal to 1, this thing does not converge. What we're trying to do with this integral is determine, what values of p makes this converge. So what we're going to do is we're just going to try this integral. So we have the integral from 1 to infinity, 1 over x to the p dx. This is going to be the limit as t approaches infinity, integral from 1 to t, so 1 over x to the p dx. So we're going to integrate this. So this limit as t approaches infinity, integral from 1 to t, x to the negative p dx. Limit t approaches infinity. And then we can integrate this now. So this is x to the minus p plus 1 divided by minus p plus 1. So just integrating, doing the reverse power rule, I'm going to evaluate this between 1 and t. This then is the limit as t approaches infinity. T to the 1 minus p over 1 minus p. And then subtract off what I get when I plug in 1. And when I plug in 1, I get, I'm going to get 1 to some number, which is 1 divided by 1 minus p. Now, so the question is, I want to evaluate this, but the limit here depends on what is the limit as t approaches infinity, t to the 1 minus p. So let's break it up into cases. Case 1. Let's do 1 minus p is greater than 0. So if this is the case, let me take a step back because I just realized. So let's assume p is not equal to 1. So the reason I'm doing that is because we've already looked at 1 over x, and I don't want to have to take into consideration, I don't want to have to take that into consideration when I integrate. So let's assume that we don't have 1 over x here. So now we have two cases. So 1 minus p is greater than 0. So that means then the limit as t approaches infinity, t to the 1 minus p. This thing is greater than 0. So t to the 1 minus p. This thing, if you look at the graphs of some values of p, this thing is going to go off to infinity. It's going to diverge. So if I have t to the 1 minus p, I could have t to the 1/2, t to the 1/3, t to the 1/4. I could even have irrational numbers in there. That's fine. then this thing is going to go off to infinity. In the case 1 minus p is greater than 0, what this is really saying, if I change that inequality around, this is p is p is less than 1. So if p is less than 1, then this thing will diverge. Okay, so now let's do the case 2. If we have 1 minus p is less than 0, and I can go ahead and solve this inequality, this says p is greater than 1. And again, I've already solved the case when p equals 1, it diverges. It's a logarithm. So if 1 minus p is less than 0, then I have p is less than 1. So we're looking at the limit as t approaches infinity, t to the 1 minus p. 1 minus p is less than 0, so it's a negative number. So this is the limit as t approaches infinity, t to the negative p minus 1. Where now p minus 1 is positive because 1 minus p was negative. So this is the limit as t approaches infinity of 1 over t to the p minus 1. And now this is something like 1 over, t to the 1/2, 1 over t to the 1/4, 1 over t, 1 over t squared. All of those functions, no matter what they are, they're going off to infinity in the denominator. So this integral ends up being 0 here. So case 1, it diverges. Case 2, it converges. And case 3, if p is equal to 1, we already saw it diverges. So that was one of the examples I did earlier. So we have then the integral from 1 to infinity, x to the p dx. So it'll converge if p is less than so if p is less than or equal, so if p is less than 1, so just follow these cases, sorry. So if p is less than or equal to 1, it's going to diverge. Be helpful to be able to see these without scrolling back up. So it diverges if p is less than or equal to 1. Okay, I see why I'm getting confused. That's not x to the p, that's 1 over x to the p. That makes more sense. So it diverges if p is less than or equal to 1. So this is something like 1 over x, 1 over x to the 1/2. So those things will diverge, but it will converge if p is greater than 1. So what that means, this is kind of abstract. So what that means is, so we have the integral from 1 to infinity, 1 over x squared dx, integral from 1 to infinity, 1 over x to the 3/2 dx, integral from 1 to infinity, 1 over x to the 10 dx. These all converge because p is greater than 1 down there. And the integral from 1 to infinity, 1 over x dx, the integral from 1 to infinity, 1 over x to the 1/2 dx, the integral from 1 to infinity, 1 over x to the 2/3 dx. These all diverge because the exponent is less than 1 there, less than or equal to 1. So this gives you a way of characterizing whether something will converge or diverge, just based on the exponent, as long as it's like a 1 over x or 1 over x to the some power. So that takes care of that. So I'm going to stop the notes. I'm going to stop the notes here. We're about to get into the second type of improper integral. So this seems like it would be a good stopping spot.